Greetings to everyone. We are Group 11 and we'll be presenting image semantic segmentation using deep learning. Image semantic segmentation is a very important part for deep learning in computer vision. The segmentation result can be used in a wide range of scenarios, such as in the field of autonomous driving or medical imaging. The image segmentation considered in this project is essentially a semantic segmentation task. In this research, we'll focus on finding an accurate way to do the semantic segmentation for images. The input will be one single image, and the output will be multiple distributions of segmentation labels for each input pixels. Due to the limitation of computing resources, we decided to implement a network with simple structure and use a very simple training strategy to achieve the result that as optimal as possible. Based on traditional convolutional neural networks, we have fully convolutional network structure. FCN can classify images at the pixel level, thus solving the problem of semantic image segmentation. However, the shortcomings of FCN are also obvious. The segmentation results are not fine enough. The result of upsampling is still relatively fuzzy and smooth, and it is not sensitive to the details in the image. And FCN only classifies each pixel separately and does not fully consider the relationship between pixels. Then come to the unit. The unit is a semantic segmentation network based on the FCN, which is suitable for medical image segmentation. The FCN network structure is modified and expanded in unit so that it can obtain accurate segmentation results with a small amount of data for training. The main idea is to add a network similar to the previous one after the shrinking network, in which the pooling operator is replaced by an upsampling operator. Therefore, these layers increase the resolution of the output. On this basis, researchers proposed the structure of the unit++. They noticed that the deep structure can capture the abstract feature of the image because of the large receptive field are more convolution operations. However, for any specific task, the degree of abstraction required is not fixed. The feature of unit is that it uses convolution to fill the long hollow part of the original unit, which allows the network to capture features at different levels and integrate them through feature superposition. This means that when a network training is completed, if a few layers can be used to output very ideal results, then the rest part of the convolution elements can be pruned during testing. Pascal VOC is one of the benchmarks of target detection technology. There are 20 categories in this dataset, including 11,000 images for training and verification, of which over 27,000 regions of interest are calibrated. Pascal VOC provides a complete set of standardized and excellent data sets for image recognition and classification. In this task, we have reclassified labels on all categories and finally made 5 labels from the whole dataset: vehicles, household, animals, person, and background. With the limited training sample, data augmentation is a good way to improve the generalization ability of the model. In short, we want to create some fake data for the model training. In the experiment of this study, we applied the following approaches to data augmentation. 1. Color transformation randomly generates changes to image brightness, saturation, and contrast. And 2. Random cropping. Use random image differences to crop and scale the image. And 3. Random flip. Flip the image with a certain chance. And also, for some segments with white pixels on their edges, we have manually treated all those pixels as backgrounds. And I'll pass to the next one.
Refer to the architecture of UNet++ to add some short-skip connections to the basic UNet architectures for reconstructing the features information lost in downsampling processing. However, after several experiments, we found that the features information of the underlying layer as the end layer of downsampling in our module, which is the convolutional layer that has the output channel of 512, may be affected by the features information of the other layers during the upsampling. So this will affect the prediction results. So we have considered adding an upsampling channel for these features informations, making them directly fusion with the UNet++ result. This channel can be seen as an end-to-end approach. We need to ensure that the module's computation resources do not grow much for completing this task. So we directly took the underlying feature information, then deconvolutioned it, and reconstructed this information to the original resolution. So our module can be divided into 4 parts. The first part is the downsampling, which is done with the pre-trained ResNet 34. We can consider this as the features extractor. The second part is upsampling process of the UNet++. We use the short skip connections and the long skip connections here to combine the features information of each layer. The third part is parallel to the second part. We use a series of deconvolutional layers to directly upsampling the underlying features information. The last part is the output, which is the classifier. We can connect the results of the second and third parts for convolution classification. Hence, the output of the module will be 5 times 320 times 320. 5 is the number of the classes, and the 320 is the side length of the input image. Then we go to the next page. There are some formulas on the slide, but they are not the actual formulas we used in the module. They are just shown to better explain our thinking. We use the Adam optimizer during the training, and we add L2 regularizations during the gradient descent calculation. The equation in the slide is a simple gradient calculation process for a linear module, and we can see that if the lambda is set to less than 1, then the delta as the parameters will be decreasing with each iteration of the calculations. The update weights during the fitting process then become progressively smaller. This is the purpose of our regularization. In addition to that, as we mentioned before, because of the reclassification of the dataset, it will not have a very balanced distribution. In order to improve the module fit, we use focal load here. The formulas on the slide is for binary classification, but multiple classification is pretty similar. We need to adjust the alpha as the weight according to the distribution of the data in each batch to make the dataset become balanced. To evaluate the module, we use 2 approaches here. The first one is a pixel level accuracy calculation as the mean average precision. The second one is MIOU, which is very common use in semantic segmentations to calculate the average overlap rate. After the experiment, we can find that not every class has the same upward trend. So next, I will hand over to the next student to discuss the results again. Thank you.
Thank you. The results in the table here show that there are relatively large differences in the performance results between different categories, which we think may be related to whether the edges of the objects are clear and stable. Person category, for example, has better results because the edges of persons are more stable and do not change dramatically due to the environment. The results of household are worse because, like the potted plants and chairs in household, their edges are not very stable. For example, chairs, they have various styles in the dataset, so it is more difficult for the model to judge, resulting in a poorer result for IOU in this category. In addition, according to the results of the figures in this page, we can find that the classification effect also becomes worse when objects are overlapping. In addition, the classification results will also become worse when objects are relatively small in the picture. This may be because the small objects have too few pixels to capture the effective feature information. resulting in relatively large error in classification. Finally, the model is relatively poor at judging edge pixel points, and many error occurs on blurred edges. We believe that this may be due to the narrow perception field of the convolutional layer. And we can expand the kernel size of the convolutional layer to improve the ability of the model to judge the edges of the object, and also add some smoothing layers to the model as well. Now go to the next page. We have also tested images outside the database as shown in this slide, and it results in a similar trend that is also observed within the test set, where the model have some difficulties in distinguishing between the class household and vehicles. From the sample results here, we can also see that the model is more accurate for person category. These results are similar to the performance of the images in the test set. Blur edges and unseen objects such as vehicles are going to affect the judgment of the model. That's all we're bringing today. Thank you for watching.